If you're like me, you're getting used to the fact that every few months, people come up with some new insane application of deep learning. You may have heard about DALL-E 2 or some other neural net that can create pretty images from text prompts. Or perhaps you've heard about GPT-3, the language model that actually helped me find the title for this video. But the neural net that shocked me the most this year is definitely AlphaCode. This is a neural net that can solve algorithmic problems of the type seen on competitive programming websites like Codeforces. Basically, in comes a text description of a coding problem, and out comes a C++ or Python program solving that problem. If you go to the AlphaCode website, you can see this beautiful visualization of the neural net generating the code. If you hover the cursor over the code, you can see what the neural network is looking at when it writes that particular piece of code. For example, at the very beginning, AlphaCode defines a variable where it stores how large the input can be. You can see that when it defines it, it's actually looking at the corresponding part of the problem description that specifies that the input size is at most 2 times 10 to the 5th. You can also see that while it writes the number, it's already looking at the relevant part of the code it's already written. And finally, the neural net increases this number by 10 just to be on the safe side. Now, this looks pretty weird at the first glance, but it's actually a common competitive programming trick that helps you against some off-by-one errors. During learning, AlphaCode saw gigabytes of code written by real programmers, so this partially explains why it chose 10 in particular. Actually, AlphaCode is probabilistic, and you can see how it wasn't very certain what to write here. It was split between adding 10, 5, or nothing. All of these choices would of course be perfectly fine. But later, there come some more difficult choices. For example, this part of the code is crucial for the solution, and you can see that AlphaCode considers doing something with one of two variables, ands and count. Here it chooses ands, but the choice only had 1% probability. So what's happening? Well, AlphaCode is actually not just the neural net. The net is used to create millions of candidate solutions, most of which are wrong. Then, there is a post-processing step that's supposed to pick the candidates for the correct solution. One part of that is to simply check which candidate programs give the correct answer on the sample input, since we also know the correct output for that sample from the problem statement. This, by the way, is how competitive programmers check their programs before submission as well. I'm sure that you would love to know more about how AlphaCode internally works, but that's not the purpose of this video. Instead, when I saw AlphaCode for the first time, I mainly wanted to understand how good it actually is. So I looked at one of the hardest problems that the AI managed to solve and tried to solve it myself. In fact, I tried to solve exactly the problem that we are now looking at. This video is mostly about this problem and my attempt at solving it. I'll come back to AlphaCode at the end. The problem I tried to solve is called buds rehanging from the website Codeforces. In this problem, we're given a tree, so a bunch of nodes connected by edges such that no edges form a cycle. This tree is also rooted, so each node except the root at the top has one parent node and possibly some children below. The nodes that have no children are called leaves. Let's highlight those in blue. So far, these are standard terms. But in this problem specifically, we also need the concept of a bud. A bud is a node that's not a root, has at least one child, and all its children are leaves. In other words, buds are basically the nodes that have only leaves as children, but are not leaves themselves. I've highlighted all of these in red. Now, we're allowed to manipulate our tree in the following way. We can take a bud and rehang it and its children to another node of the tree. Let me actually do that one more time in slow motion, just so that you can see that in this case, after we cut the bud off the tree, this node becomes a new bud, and after we put the bud back, the nodes above it are no longer a bud and a leaf. And now the question is, you're allowed to do these operations any number of times with any buds you choose. If you do the operations as cleverly as possible, what's the lowest number of leaves the tree can have? In our example, the number of leaves at the beginning is 7. You can see how it changes when we do the operations, and the lowest we can get seems to be 5. Because this is a coding problem, it's also important how large the input data is. In our problem, the tree can have around 10 to the 5th nodes, which means that the algorithm we design needs to have close to linear time complexity. And there are examples in the problem statement to make all of this clearer. Let's look at the first one. The tree looks like this. It has 4 leaves, but if we rehang this bud here and this bud there, we get a tree with 2 leaves, which is the correct answer. So this is the problem. In a few seconds, I will describe my attempt at solving it, but now I encourage you to pause the video and think about it for yourself. You now have the excellent opportunity to see if you can match AlphaCode's solving skills. In competitive programming problems like these, it's often useful to first play around with the problem and get a feeling for what the correct direction might be. So, I first drew an example tree that looked roughly like the example we already saw. Then I spent a lot of time just playing with the tree, simply to understand what the rehanging operations are doing. And after some time, I realized the following thing. Let's look at, say, this bud, and enclose it and its leaves in this pointy oval. Then do some random operations, and you can see that the bud and its leaves always stay together. They never separate. And that holds in general. I realized that I can repeatedly cut the buds from the tree in any order and rehang them below the root like this. Now I draw my pointy oval around each bud and start doing some random rehanging operations. You can see how the nodes in the same oval always stick together. Okay, so all the rehangings we do are just shuffling the 4 buds around, and the buds cannot be split. When I understood this, I asked the following question. Let's say I take the 4 buds and stack them below the root in a different configuration, let's say like this, to get a new tree. The question now is there always a way to start with the original tree and use my rehanging operations to end up with the new tree? Well, it turns out the answer is yes. Why is that? Well, one way to see it is to use my special tree where everything hangs from below the root as an intermediary. I can convert my starting tree into this intermediate form, but the same also holds for the final tree. If I now revert the operations that convert the final tree into the intermediate form, I get a way of converting my starting tree into the new one. So, we proved that the rehanging operations can create any possible configuration of the buds. By the way, using this simple tree as an intermediary is an instance of a more general trick that's sometimes useful in math or competitive programming. For example, let's say I ask you to come up with a sequence of moves that brings this scramble of the Rubik's Cube to that one. Well, if you can work out how to solve both the first cube and the second one, you can simply revert the second solution, put them together, and you have the solution. In both cases, we want to transform one complicated object into another one, and the trick is to just find 2 transformations from a complicated object into a simple one. But that was a digression. Let's go back to our problem. By now, we actually understand perfectly what the deal is with these rehanging operations. In fact, this whole rehanging business was just a cruel trick that the problem setter played on us. When we get the input tree, we can forget all those rehangings and just split the tree into buds. The trees we can construct using rehangings are exactly the trees we can construct by stacking the buds below the root in any order, like this, or this, etc. Okay, so now is a good time to recall the problem we actually want to solve. We want to minimize the number of leaves. Do you see how we could do that? Well, whenever we stack 2 buds on top of each other, the bottom bud covers 1 leaf from the bud above it. So, if you think about it, one possible solution is to just stack the buds on top of each other like this. Nice, so that means there's an easy formula that computes the answer. We first split the tree into buds. Then we count the number of all blue nodes and red nodes, and compute the answer by taking the number of blue nodes and subtracting from it the number of red nodes minus 1. The -1 is because one red node has to hang below the root, and each remaining one can cover one blue node. That sounds great. Let's quickly double check our formula on the tree from the sample input. First, we find the buds in that tree and color them with red and blue. But now this is a bit different because after we isolate all the buds, there is still one leaf hanging from the root. I colored it blue because together with the root, it is kind of forming one more bud. But the root itself is gray because by definition, the root can never be a bud. So there are 4 blue nodes in our tree and there are 2 red ones. This means that our formula says that the answer should be 4 minus 1, which is 3, because we can hang the buds like this and get just 3 leaves. But this is not correct, because we can actually rehang the buds like this. In this way, each of the red nodes covers one blue node, so the answer is just the number of blue minus the number of red nodes. So we actually need 2 formulas for the 2 different cases, based on whether after removing all the buds from the tree, we are left with just the root, or if there is some other leaves hanging from it. Is this solution correct now? Well, there is a simple way to check. We just write the code, submit it to Codeforces, and nice, it works. Okay, I hope you enjoyed that problem, but now let's go back to AlphaCode. In competitive programming, you can sometimes solve problems without fully understanding what's happening. In the case of AlphaCode's solution, the code is mostly a very clean implementation of our solution, but there is one weird part where it sorts the edges around every node according to their depth for some reason, and then it doesn't use this information at all. If you comment out these lines in the code, it still does the same thing. So I'm not convinced that AlphaCode fully understands what's going on. Well, whatever the word understand means in this case. Also, this was one of the hardest problems that the AI managed to solve. Sometimes AlphaCode fails in entertaining ways on much easier problems. For instance, this is a much easier problem that AlphaCode couldn't solve. Its solution contains this part. You can see how it just hardcodes the answer to the sample tests into its solution just to pass them. Obviously, that doesn't generalize very well. Have a look at the website linked in the description. It shows more examples of the code generated by AlphaCode, so you can use it to make up your mind about whether AlphaCode is insane or just cute. In my opinion, AlphaCode is extremely impressive. I've already got used to the fact that neural nets are pretty good at the stuff that we, people, can do without much thinking, like distinguishing between dogs and muffins. But what AlphaCode and other AIs from the past few years show is that neural nets can go beyond that. Solving problems like those that AlphaCode did really seems to require some kind of reasoning. You could see how I really needed to think a lot before coming up with a solution. So I think it's a pretty safe bet to expect that neural nets will be able to do some pretty mind-blowing stuff in the near future. But in the next few years, before AI takes our jobs of explaining computer science topics, we will continue doing that for you. Bye bye!